Okay, so today we're going to be doing the box on a ramp type question. So it reads like this. You are lowering two boxes, one on top of the other, down a ramp. You're pulling on a rope parallel to the ramp surface. Both boxes are moving together at a constant speed of 0.2 meters per second. The coefficient of friction, which kinetic friction, for the lower box in the ramp is 0.444, and between the two boxes is 0.8. We have the ramp angle. The question asks, what is the magnitude of the force applied? And we have a little picture to the left here drawn with our ramp, our two boxes. One is heavier on the bottom, lighter on the top. We've got theta, and we want to know what is the force applied. Okay, so we're gonna try and get some free body diagrams going here. We can start drawing one for the smaller box, and then beside it we can draw one for the larger box. Now, a trick when you draw these things, you can draw like these imaginary axes that pass through them. I usually use some dashed lines here. So we've got our typical y and x axes, but this is a ramp question. The ramp is not a x and y axis, it has like these slanted ramp axes. So what if we go ahead and just draw those slanted axes in like this? These will come really in handy, guys, so I recommend you guys draw these. Awesome. Okay, so just for clarity, theta is the angle, I'll draw it here, between these two axes. Theta is also the angle between these two, and these two. So you guys can think about it like you take a plus sign or like a crosshair kind of, and you've just rotated it so that your new axes are theta apart from each other. And then the exact same thing for this picture. This is going to be kind of a long problem, guys, so I'm going to try and break it up into two sections here. Okay, so let's give the boxes some numbers just for organization. So this is 1 will be the top box, and 2 will be our bottom box here, right? Okay. Awesome. So I'll show you guys the way my physics teacher always told me to draw these free body diagrams. What you do is you go start at the top and you dance around the object, see if anything is touching it, and then you throw in gravity. So we start at the top and there's nothing touching it, and then wham, we hit this bottom box. Okay, so bottom box means we can add this force normal, right? There we go. So just for simplicity, I'll just call this N here instead of Fn or whatever, right? Okay, and this is force normal 1, so N1. Awesome. Okay, so we notice that normal 1 is pointing perpendicular to this ramp surface, right? This ramp surface is drawn by this dashed line, so perpendicular would be that other dashed line that we draw. Guys with me so far? You're like there's a lot of dashed lines here. Okay, let's keep going. So another trick I do is whenever I draw a normal force, I always try and draw the force of friction if there is one. And in this case, there is one, right? There's a static friction holding the two boxes together because they're sliding together, right? Okay, which way does the static friction act? That's tricky. We know it acts parallel to the surface, so it'll be somewhere along this dashed line here, but we don't know whether it points up the ramp or down the ramp. So here's what we can do. We know that friction will oppose the attempted motion, so what if we draw in all the other forces and then we just add friction last? And that's exactly what we're going to do. So we draw the gravity for this. We'll just call it, this will be M1G, right? Fg equals mg, right? Okay, and this is all the forces that are touching it, because if we continue our dance, we get back to where we started, so there's nothing left, right? Awesome. So which way does the friction act, guys? Well, here's a trick. We're told that they're moving together at a constant speed. If they're moving at a constant speed, that means there's no acceleration, that means there's no net force, which means all the forces have to balance. Well, have a look, guys. If we look at our slanted axis here, this is our slanted y-axis, and this is our slanted z-axis. Let me draw that in. Slanted y-axis and our slanted x-axis. The slanted y components could be balanced because this one's pointing in y, this one's pulling down, a component of this is pulling down in y. But look at the x components, guys. We have an x component pulling to the left, but then this one is neutral. It has no x component. So therefore, we need our force of friction to be going up the ramp. So we'll call this Fs, like this. Okay. And did you guys understand why? Because we need to balance all these forces so that there's no net force. If this force of friction was pointing down, then look, we would have a component pulling to the left here and another component pulling to the left. Well, two lefts can never cancel each other out, right? And that's all for this small box, guys. So let's look at this bigger box now. Okay, do you guys remember Newton's third law? For every action there's an equal opposite reaction, right? So those are talking about forces. So what we can do is we can put our Newton law pairs right even before we start to look at the thing too carefully. So look, we had a normal force 1. Where was it pointing? It was pointing up our slanted y-axis. This is y, this is x. So up the slanted y-axis. So then it has to be an identical force pointing down, right? I'll circle them for you in case we need to look at them later. What else is a Newton force pair, guys? Look, this Fs is a Newton force pair. This is pointing up this slanted x, so this one has to point down this slanted x, right? And again, I'll put a box around this one so we can identify these force pairs later. Okay, very good. Those are all the force pairs, guys. So now we do the dancing thing, right? So let's dance. We start here. Oh, already we have something touching it. We have what? We have the top box touching it. But we already took care of that because we already got normal force 1, right? And the friction, we already took care of that. Okay, so the top box is good. We can almost look at the picture as if it was just like this kind of picture, right? Which we can all do. This is pretty easy now, right? So we've got a big box on a ramp. So we've got a normal force from the ramp, right? So we'll call that N2, and that's going to point up our slanted y-axis, and it's going to be perpendicular to the ramp surface, right? What else? Okay, we've got this force applied here, right? That's what we're trying to solve for, this Fa. And we've got gravity, but we're not there yet. We have to keep dancing. We've got this ramp, right? So we've got the normal force. Okay, guys, remember what I told you? Whenever we have a normal force, we have friction. What kind of friction between this box and the ramp? Kinetic friction. Good. Which way does it point? I want you guys to maybe pause the video for a sec. Which way does the kinetic friction point? We know it has to be on this surface, but is it going to point down or up? Very interesting question, guys, because think about it. We know that friction is supposed to oppose the attempted motion, and we know that we're supposed to get all our forces balanced because we have no net force, but I mean all these forces, this is like north, south, east, west, they're kind of already balanced, right? So we have to think about it carefully. It's trying to oppose the attempted motion. This is where you have to read the question very carefully. Right here. I messed this up the first time, actually. It says, you are lowering 2 boxes down the ramp, which means this whole system is sliding down the ramp. It wants to try and slide down the ramp. If friction is opposing that, then friction is going to make it slide up the ramp, or it's going to try and make it slide up the ramp. I'm getting kind of squeezed here, but this is FK, in case you can't really see it on your screen. That's FK, and then that's FA. So the kinetic friction is going to pull up. So in fact, the kinetic friction is working in our favor, right? It's making us pull not as hard. If we had to put in 100 newtons without the friction, maybe we only have to put in 50 now or something. So it's making our job easier. Okay, guys, and that is it for the free body diagrams, right? Oh, no, remember, we always have to add in gravity. Don't forget about gravity, guys. That's a quick sanity check you can always do at the end. Okay, yes, that's much better. So that's all for the free body diagrams. So I'll zoom into these if you guys want to maybe have a closer look at them. There we go. Now you guys can see what I was talking about, right? So this is the bigger box, right? This is referring to this 48 kilogram box right here on the ramp. And then this smaller box that we drew is referring to this smaller box that's on top. Okay, guys, so you can have a look at those for a quick sec. Maybe pause the video if you need to copy it down or something. And I'm going to make this into a 2-part video, actually. So I'm going to end the video right here with these free body diagrams. If you've gotten this far, you did better than probably most of your classmates, because those Newton's third law force pairs were kind of tricky to sort out, guys. So in the next video, we're going to be jumping into the equations, and we're going to be subbing in and solving, and I'm going to be showing you guys how you need to have an equal number of unknowns and equations and stuff. See you then.